Hi everyone, my name is Arif Malik. I am part of the AMP navigation team, and I'm here to present our work over this semester, which is a waypoint-based approach to autonomous racing. So let's kind of get into what that means and what we're doing here. So first thing first, as a general idea, a lot of people in autonomous racing and just self-driving cars in general know that at the end of the day, the car needs to be able to predict steering angle and throttle. The same way that you drive a car by controlling a steering wheel and the gas pedal accordingly. What we realize is that the approach to actually generating those is very difficult. We try to train a network just to simply predict a steering angle and a throttle, and it has very poor generalization. It can't really think in every sort of situation. And so we wanted something that was closer to the human mindset, and the way we got to that point was actually by an NVIDIA paper. They control the car by simply generating paths. And you can kind of see that there's one path here, there's a curved path here, and a curved path here. And we were very inspired by that. We thought that what if we could actually control a car that way? And so that kind of brought us to our work this semester. What we've been doing is that we've been able to turn our simulated game environment into a sort of pathway generating thing by associating every image with a certain set of coordinates. And we're training our neural network to predict those set of coordinates successfully. And with those coordinates, we send that back to the simulator. And what the simulator does is that it'll turn those 10 coordinates into a appropriate line or curve to drive upon. Now that it's easier said than done. And before I kind of go into a demo of the network, I'd kind of like to talk about how it actually predicts these lines. So if you want to see right here, this is what we call the network architecture. And the way it works is that, say this is the image that the car gets, right? There's no sensors, there's nothing else, just an image. A little bit of processing, meaning that they'll kind of start to exaggerate some features, was sent into the first couple of convolutional layers. And what those convolutional layers do is that they start to bring out features. There's certain things that stand out and are unique about certain frames, and the network will at least have that data to work with. And so after these 5 convolutional layers, we have a bunch of features that we can pick from. And so the last thing that we do before we output the set of coordinates is that we send them through these fully connected layers. And these fully connected layers are able to start to pick apart that there's certain features that I know are going to be essential to the output that I want. And so what that means is that going from 300 features, they know that those 300 features will result in 30 values. And it'll help to associate those 30 values with any given image. And so the reason why we chose 30 is because each XYZ coordinate is actually 3 values, and 10 XYZ coordinates would be 30 values. So our network at the end of the day predicts that list of 30 values to send back to our simulator to drive upon. So let me demonstrate that before I do anything else. So what you're seeing right now is that there is nothing else that this car has that you and I don't have. All it's driving upon is just some imagery, and then it's predicting these sets of coordinates that you see right here. And it's doing a pretty good job. I should say that all this car has been able to learn from is just 2 minutes of driving data. We only recorded 2 minutes to train this initial model, and it's doing a pretty good job. It'll even be able to round the corner before it falls off. And I'll cut it off a little bit before that just to wrap up, but it's not bad for a couple of teenagers, right? Yeah. You can see that it's already been able to learn from the features that white line it has to kind of stay away from. Both of these white lines. And so yeah, I'll close this up and I'll wrap up. So going forward, we've kind of been able to prove that we're able to have this waypoint generalized path to drive upon, and it can do it pretty successfully. So looking towards the future, we kind of want to take it further into the racing environment. We wanted to be able to detect race cars, we want to be able to overtake race cars, and we definitely need more data in order to do that. Now, like I mentioned earlier, the 3 leaders of this team, me, Mikhail, and Alec, whose network you just saw, we're 3 freshmen, just 3 teenagers, 18, 19-year-olds, and we're definitely looking for some more resources like high-performance computing, so we don't have to train these networks on our own computers, and definitely some ways to automate the training process so we can take it even further. With that being said, we're incredibly grateful to Dr. Gamal, Shakti, Yaya, and Sham for helping us so far, and we really hope that we can take this network to the fullest extent, maybe even bring it into the actual autonomous racing challenge. So with that being said, from every member on AMP, I would like to say thank you for tuning in and have a good day. Bye.